the entire procedure from beginning to end. A medical research team decides to study whether pressure exerted on a person's upper arm will increase bleeding time. The average bleeding time for a pricked finger where no pressure is applied to the upper arm is 1.6 minutes. Now that 1.6 applies to the population mean. To test their claim, the research team randomly selects 64 employees. They find that the average bleeding time is 1.9 minutes with a standard deviation of 0.8 minutes when 50 millimeters of pressure is applied to the upper arm. So, important information is highlighted in red. 1.6 is a population mean. Even though it doesn't use the word population mean, you're told it's an average, which is essentially a mean. The sample size is 64. The average bleeding time for the sample, or the mean of the sample mean x bar, is 1.9 with a standard deviation of 0.8. So that implies that the standard deviation for the sample is 0.8. So we have our sample standard deviation. Now, the direction of the test is going to be found when you note that the medical research team decides to study whether pressure will increase bleeding time. We have the average bleeding time when no pressure is applied, but we want to test if applying pressure will increase bleeding time. So this test, increased bleeding time, meaning greater than 1.6, is going to be a test on the right side. Does this sample result support the claim that pressure applied to the upper arm will increase bleeding time using an alpha of 5%? So we're going to go through this test assuming that applying pressure to the upper arm has no effect on bleeding time. So we're going to assume that applying pressure increases bleeding time no more than 1.6. It will be roughly that of the population. We make that assumption in the null hypothesis, and then our goal is to disprove the null hypothesis with strong sample evidence. If we can prove that the sample evidence, the sample mean, is significantly greater than 1.6, we have enough evidence to reject the null hypothesis, which states that applying pressure does nothing. Applying pressure, in this case, would actually do something if we can reject the null hypothesis. It would increase bleeding time. So we go to formulate our hypotheses, and whenever we start the formulation of hypotheses, we always begin with the phrase, the population mean. So for the null hypothesis, we state that the population mean bleeding time when 50 millimeters of pressure is applied to the upper arm is 1.6 minutes. Okay, so we have to start with the words the population mean, and then we have the variable, which is bleeding time when 50 millimeters of pressure is applied to the upper arm, and then we say is and the value, 1.6. So HO, again, the status quo, the assumption that applying pressure does nothing to the bleeding time. So we make the assumption of HO being true, that applying pressure has produces a mean bleeding time of 1.6 minutes. So mu is 1.6 symbolically. That's our claim. Then our counterclaim against this null hypothesis is that the population mean bleeding time when 50 millimeters of pressure is applied to the upper arm is greater than 1.6. It's pretty much set up the same way as HO, with the one exception. When you specify direction here, instead of saying it is 1.6, we say it is greater than 1.6. So our alternative hypothesis will always state a direction, either greater than or less than. A null hypothesis will simply state the value. It is 1.6 minutes. So the symbols for our alternative hypothesis is mu greater than 1.6. Once you have the null and alternative hypotheses set up, you are asked for the mean of the sampling distribution and its correct symbol. Like last time, The mean of the sampling distribution is let's back up a bit. Like last time, our sampling distribution is a collection of sample means. This hypothesis test is using a sample mean in an attempt to disprove a population mean. And so, when we model this, we have a collection of possible sample means, which essentially is the sampling distribution of sample means. The center of that, or the mean of that, is mu sub x bar, and its value is always equal to the mean of the population, 1.6. So the hypothesis test in the last lecture and the hypothesis test in this lecture always state that the mean of the sampling distribution is mu sub x bar and its value is 1.6. Okay, so this is just simply a way of us to identify the center of our bell curve, the center of our distribution. Is it going to be a normal distribution or a t-distribution, this test, and why? This time it's going to be a t-distribution, and the reason is we do not have sigma. Sigma is not known. So you can either use the words sigma, you can use the word population standard deviation, or you can even use the symbol for sigma, but you must state that the reason why we're using the t-distribution is because sigma is not known. So when a problem does not provide you with the population standard deviation, you use the t-distribution, and that indicates that you're going to use t-test on your calculator eventually when you get to that point. Before we move to the calculator, though, we have to come up with our decision rule. When we look at this test in the bell curve, we note that alpha is 5%. Our greater than test indicates that it's a test on the right side of the bell curve. So we get started by shading in the upper 5% of area for alpha. The center of the distribution is 1.6. Mu sub x bar is 1.6. The vertical line here is the dividing line between rejecting the null hypothesis and failing to reject the null hypothesis. If you happen to get in this test an x bar, a sample mean, that is to the right of the vertical line, it will produce a p-value that's smaller than 5%, because the p-value will be the area from that sample statistic x bar all the way up to positive infinity. Now, if x bar is to the right of the vertical line, then that area must be smaller than alpha. Must be smaller than the top 5%. In which case, you can reject the null hypothesis. But if you get a sample mean that doesn't fall past the vertical line, if it falls over here, it's going to produce a p-value that is greater than alpha, because the p-value will be the area all the way from that x bar to positive infinity, which is then going to be bigger than this top 5%. So the decision rule is reject HO at alpha equal 5% if the p-value of the sample statistic is less than or equal to 0.05. We are always going to reject the null hypothesis if the p-value is smaller than alpha. We always want a p-value that's smaller than alpha if we want to reject the null hypothesis. Okay, it doesn't matter what side of the bell curve the test is on, this is always going to be the same. We always want a p-value that's smaller than alpha, so less than or equal to 0.05 in this case. We look at our sample data. In this example, the sample statistic is given as x bar, sample mean. So the symbol is x bar. The value of that sample statistic, the value of x bar, is 1.9. So going back to the words of the problem, you'll read that the sample mean is 1.9. If you locate 1.9 on the t-distribution, on the bell curve, you'll see that 1.9 is somewhere to the right of 1.6. And when we find the p-value for 1.9, we will be finding the area from 1.9 all the way up to positive infinity. And we have to compare that p-value to alpha, and ideally we want it smaller than alpha to reject the null hypothesis. So we go to our calculator to find the p-value. Let's remember the x bar is 1.9, and in this problem the sample standard deviation is 0.8 and the sample size is 64. Okay, so you're going to go to your calculator and put in the important information from the words of the problem. Okay, our calculator. To wait for it to open for a moment. You're going to go to the t-test menu, or the t-test function, which is in stat calc tests. Once you're there, you'll see that you need to input all the important information that you see highlighted in red. Okay, so I'm going to quit the screen that I was just on. I'm going to press Stat over to the test menu. Okay, number 2 is the t-test, so go down to number 2, hit enter. What makes this test different from the z-test is the t-test asks you for Sx, which will be the sample standard deviation, and the z-test asked you for sigma x, which was the population standard deviation. So you know that you're in the right test because it's asking you for the values that are given to you in this particular problem. So we put in mu sub 0 of 1.8, the population mean. No, 1.6, the population mean. Okay, sorry. 1.6. Let me just delete a couple of extra things I have there. Okay, your sample mean 1.9. Your sample standard deviation 0.8, which is the same as 0.80. Your sample size 64. The direction of the test is on the right. It's the alternative hypothesis uses the words greater than, so greater than mu sub 0. And then go down to calculate and hit enter. Okay, so we have a p-value. P equals 0.0013. That's the most important thing that we want to get out of this screen. We do see a couple other pieces of information. The t-score is given to us as 3, which we're not going to use in this test. And then x bar and sx and n are reiterated, 1.9, 0.8, and 64. But we have to take note of the p-value to 4 places, 0.0019. So going back to our test here, okay, to 4 places we have a p-value of 0.0019, and now we're ready to make our conclusion. If we note that alpha is 5%, but the p-value for x bar is 0.0019, you should note that 0.0019 is smaller than 0.05. So p is smaller than alpha. The p-value is smaller than alpha. The p-value fits inside alpha. The sample statistic 1.9 is very significant. Anytime you have a sample statistic with a p-value that's smaller than 1%, we say it's very significant. If it's between 1% and 5%, we say it's significant. If it's greater than 5%, we say it's not significant. This p-value is smaller, which is ideal, because now we know that we are in the reject region of the bell curve, and we can reject the null hypothesis. So our conclusion, in general, if we have a p-value that's less than alpha, we reject the null hypothesis and accept the alternative. That's your rule. So in this particular problem, the conclusion is reject HO and accept HA at alpha equal 5%. So when you write your conclusion, you're going to write you reject HO and accept HA at the alpha that was provided in the problem. The two types of conclusions are either going to be reject HO and accept HA or fail to reject HO. You only have two conclusions in a hypothesis test, and this is one of them. The question that was posed, does the sample results support the claim that pressure applied to the upper arm will increase bleeding time? So now you have to understand what you just found in this hypothesis test. You rejected the null hypothesis. The null hypothesis stated that putting pressure does nothing to bleeding time. Putting pressure on the upper arm produces a bleeding time that's the same as the population bleeding time 1.6. So understanding what the null hypothesis really stated and understanding that you've now just rejected the null hypothesis, does the sample result support the claim that applying pressure will increase bleeding time? So you should say yes, the sample result supports the claim that pressure applied to the upper arm will increase bleeding time. Okay, you should recognize that when you rejected the null hypothesis, you rejected that bleeding time was 1.6 when pressure is applied to the upper arm. Now, if you need more of an explanation, because what I have here is sufficient on an exam, just yes, the sample result supports the claim is fine. However, if you need more of an explanation, you can refer to this. By rejecting the null hypothesis, you're rejecting that the population parameter is 1.6 when applying pressure to the upper arm. That should be 1.6 minutes. We accept that it must be greater. Okay, so when you've rejected the null hypothesis, you rejected the 1.6, therefore it must be more than 1.6. And that is a hypothesis test in its entirety when you don't have the population standard deviation. We have two more examples, very similar, but at the end of both of these examples, we're going to take a look at type 1 error and type 2 error, which can be a little tricky to understand.